We're surrounded by vector quantities in physics, and we use them to solve problems all the time. One of the techniques we used is to split up those vectors into components. In this video, we're going to look at an example on how vector components can be used in dynamics or force problems. In subsequent videos, we'll look at how we use vector components through our other lenses. In this case, we're dragging a box across a floor with a rope. How would you draw the free body diagram for this box? And what coordinate system would you use? And how would you break up the forces to fit within that coordinate system? When drawing the free body diagram, I ask myself what's touching our box. The normal force from the floor pushing up on the box. Let's go with a frictionless surface right now. So there's no friction force here. The string is also touching the box, and gravity can reach in from a distance. When solving dynamics problems, there's one very important question we like to ask ourselves. What direction is the acceleration? In this case, the acceleration would have to be to the right. I always try to pick the direction of the acceleration as one of my directions in my coordinate system. So I would pick this as being parallel to the acceleration, and my other direction would be my perpendicular direction. Why do I always do that? Because the parallel direction has all of the acceleration in that direction. That means the perpendicular direction has an acceleration of 0. And it's much easier to solve when I have one equation that equals 0 than if I have two equations with neither one equal to 0. So that would leave me a t parallel, a t perpendicular, a normal force, and the weight of the object. If we're given this angle, then we can solve for t parallel and t perpendicular. Now we apply Newton's second law, sum of the forces equals ma. This is a vector equation. We split it up. If we're breaking up our forces into parallel to the acceleration and perpendicular to the acceleration, we can break it up. Sum of the forces parallel to the acceleration is equal to m times a. That's just the acceleration of our object. And some of the forces perpendicular to the acceleration have to be 0. There is no acceleration in that direction. That's why we've aligned our coordinate system this way. So that would be my positive direction. And I get t parallel equals ma, or t cosine theta is equal to ma. And you shouldn't need a calculator and figuring out cosines of the angle to figure out that as we reduce the angle, if we pull with the smaller angle instead, same magnitude of tension, what's going to happen to our acceleration? It's going to increase, isn't it? And if we instead pulled with the steeper angle, with the same magnitude of the tension force, our acceleration is going to be smaller. We have less force pulling our box to the right than we have if we pull with a more shallow angle. You should have some intuitive feel for how the angle will change the acceleration. Now, why do I need to do this direction if there's no acceleration there? Well, I do that to find the normal force. Why do I need the normal force? Because typically I have friction in my problems, and I need the normal force to find my friction force. In this case, there's no friction, but let's find the normal force anyway. If up is my positive direction, I have a normal force in the positive direction, t perpendicular in the positive direction. The weight of the object, the force of gravity, in the negative direction, and those all have to sum to be 0. So my normal force is equal to mg minus t sine theta. That means that the normal force isn't holding up the whole weight of the object. The floor does not have to hold up the whole weight of the object, because part of the pulling force from the string, if we break up the string into components, part of the pulling force of the string is holding up some of the weight of the box. So the floor doesn't have to hold up as much. If the string wasn't there, what would the normal force be equal to? The normal force would just equal the weight of the box if there was no string pulling on it, if the string wasn't there. But because the string is pulling, and it's pulling up at an angle, kind of helping to lift the box off the surface doesn't have to hold up as much weight. And you can get a feel, an intuitive feel, for how the normal force changes as we increase this angle. If we pull almost straight up with our tension force, the normal force is going to get smaller and smaller as we pull with a steeper angle. The force of gravity is not going to change. But the bigger the component of the tension in the vertical direction, the more the tension will hold up the weight, and the normal force will be less and less. If we make the tension too big, where it wants to lift the box up off the surface, well, we know a surface can't pull on something, it can only push. So at some point, if we keep making the tension force bigger and bigger and bigger, we'll lift the box up off the surface and we'll get acceleration in that direction. But let's not go there. Let's keep our box moving on the surface. So just to recap, when you see a situation like this, forces going in different directions, and you're trying to find how you're going to set up a coordinate system and split your vectors up into components. You might wonder, why didn't I choose this direction as one of my directions in my coordinate system, and then this direction as the other direction? And then I could have broken up the normal force and the weight into components to fit it into that coordinate system. Well, if you did that, both directions would have acceleration. And so you'd have two equations, neither one would be equal to 0. It would be much more difficult to solve that problem. Always ask yourself, what direction is the acceleration? Then you align your coordinate system with that direction, and your perpendicular direction is perpendicular to that. All your acceleration is in one direction. I call that my parallel direction. You could call it your x direction if you want. But we're not always horizontal and vertical. Sometimes we're on an incline, or we have a mass hanging and moving up and down vertically. So I like to use parallel and perpendicular. Let's take a look at an incline real quickly. Here's the exact same problem. We're pulling on our box with tension T. It's at an angle theta with respect to the slope of our incline. And what directions would we choose as our coordinate system? Well, you'd ask yourself the very important question, what direction is the acceleration? If the acceleration is in this direction, then you would want to align your coordinate system with that direction and perpendicular to that.